To understand a material's properties like the hardness of a diamond, the conductivity of a metal, or how a new drug interacts with a virus, we have to study them at the atomistic quantum level. But when you zoom in, deeper, past the orderly lattice, you don't see simple clockwork. You see chaos, a swarm of electrons, buzzing, interacting, pushing and pulling on each other, where each particle interacts with every other particle in a complex, chaotic way. This is extremely hard to simulate. The Schrödinger equation becomes too complex. The Hamiltonian becomes effectively impossible to solve the moment you go past just a couple of electrons. Specifically, an exact mathematical formula is only possible for simple one-electron systems, like hydrogen. For anything larger, we have to switch to numerical methods, solving the interactions by brute force. But even with massive supercomputers running for weeks, this approach hits a dead end at just a few dozen electrons. The computational cost doesn't just grow, it explodes exponentially. The scaling hits a vertical wall. So how can we study theoretically a material when even the smallest material's unit cell contains a couple of atoms and dozens of electrons? That sounds small, but for the exact Schrödinger equation, that is already game over. We hit the computational wall before we even finish describing the smallest building block of a crystal. So instead of solving the impossible, we cheat. We stop trying to track every single electron's position, every movement, and every interaction with every other particle. Instead, we shift our focus to something simpler, the electron density. We discovered a fundamental truth. If you obtain the electron density of a system, you don't need the exact wave function. The density alone holds the key. It lets us retrieve all the important properties, energy, structure, forces, without ever having to solve that impossible full Schrödinger equation. This is the key to density functional theory, and it is why DFT is the absolute workhorse of modern science, the most popular computational method in quantum chemistry and material science today. If you look at the top 100 most cited scientific papers of all time, you won't just find biology or medicine, you will find DFT. In fact, 12 of the top 100 papers in history are dedicated to this exact theory. And the computing power, it runs the world. Some estimates suggest that roughly 1/6 of all supercomputing cycles on the planet are spent doing just one thing, solving this equation. So how can we calculate the electron density without solving the full exact Schrödinger equation? If we try to calculate it directly from the chaos on the left, we are stuck. The answer is, we replace the complex, interacting real system with a fictitious, non-interacting one. This is known as the Kohn-Sham system. We imagine a model where electrons do not repel each other. Instead of a chaotic swarm, they move independently, guided by a single background field called the effective potential. Because the electrons are non-interacting, the math simplifies dramatically. The impossible many-body problem collapses into simple single-particle equations. But here is the brilliance of the theory. This effective potential is constructed to implicitly contain all the complex interactions, the quantum mechanical exchange and correlation effects. This ensures that the electron density of this simplified fake system is mathematically identical to the density of the real system. It is a mathematical mirror. We solve the simple, non-interacting equations, and we retrieve the exact physical density of the real material. But there is a catch, a chicken and egg paradox. To solve these simple equations, we need to know the effective potential, the landscape the electrons move in. But that potential depends on the electron density, and we can't know the density until we solve the equations. The input requires the output, and the output requires the input. So how do we break this cycle? We don't solve it in one go. We iterate. We use an algorithm known as the self-consistent field loop. Step 1, we guess. We make a rough approximation of what the electron density might look like. We feed this guess into the equations to construct a trial potential. Step 2, we solve. The computer calculates the electron paths in this trial potential and gives us a new density. Then we compare. Is our new density the same as our guess? Usually the answer is no. So we take this new density, update our potential, and run the calculation again, and again, and again. Guess, solve, update. With every cycle, the error shrinks, the density settles, until finally, the input matches the output. The system is self-consistent. We call this convergence. The loop stops, and what we are left with is the true ground state of the material. We have captured reality. Now you might think, guessing and checking over and over? That sounds slow. But compared to the alternative, it is light speed. Just look at the difference. On the left, we have the exact Schrödinger equation. Because every electron talks to every other electron, the complexity is exponential. But now look at DFT on the right. Because we solved for the density using our loop, the scaling becomes polynomial. That vertical red wall collapses into a manageable green slope. Suddenly, that 50 electron limit is gone. We can simulate small proteins with 500 electrons. We can model nanoparticles with over 1,000 electrons and materials with up to hundreds of atoms. And this shift changes everything. Because when you can simulate reality this fast, you stop just observing nature and start engineering it. We used to just search for materials. Now we design them. That is how we cheat the impossible. That is the power of density functional theory.